Okay, so let me start again. Thanks a lot to ISRO for inviting me to give you a talk during the start program. I think it's a fantastic program, and I wish it all success. And I hope all of you have a really good time listening to the lectures as well as answering the questions we all prepare for you as a quiz after the talk. Uh, of course, one small correction to what Meghla said. I used to be the chair of the AFAS Outreach Committee, no longer. I work at the Indian Institute of Astrophysics. I don't know how many of you have heard of it. It's headquartered in Bangalore and it has observatories all over India. And I'll tell you a little bit about the institute as well as Indian astronomy towards the end of this talk. I titled this talk as From Astronomy to Astrophysics Part. I will do the second part later next week. The reason I titled it so is that people usually think astronomy and astrophysics are the same thing, and to a large extent, I think one can interchange the two terms. Except that I would like to make a small distinction as astronomy being the study of the sky based on observations and it's usually restricted to positional astronomy. How do things move? What are their positions and so on? And astrophysics is what happens when you apply physics to your observations. And therefore, I would like to make this small distinction. The first part of the talk will be astronomy leading towards understanding phenomena we see with our telescopes. And the second part will be more astrophysics itself, where I take three or four basic principles and illustrate how they've been used in astronomy to understand the universe. So with that, let me start with a very, very basic introduction, but I think it's good to have a perspective as to what astronomy is. Astronomy, as you know, as you might imagine, is one of the oldest sciences because long back the skies are very dark, and if you look up at the sky at the night, you see fantastic things, things which are bright, shiny, things which move in the sky, things which suddenly appear and disappear, and humanity has always wondered what they were and have tried to understand them and predict them. Right? So slowly people started looking at how the sun moves, how the stars move, how the moon moves, how the planets move, and they started detecting patterns in the movement. And they tried to see if they could use these patterns to predict how the sky would be later. And this was important in earlier times of all cultures because you needed to predict the weather, you needed to predict when summer would start, when the harvest season would start, when do you have to sow your crops, when would certain festivals be, when do you, if you're nomadic, when do you migrate to a warmer region, etc. For all of this, one needed to the predict or measure time over a period of weeks or months, and therefore astronomy was important because that is the way people could mark time, right? But of course, a lot of astronomy events are sudden. For example, eclipses or comets and so on. And because people did not know what they were for many hundreds, if not thousands of years, they were also a cause of fear and confusion in every culture, right? So there were stories about how they were harmful or sometimes how they were good for us and so on. And as we knew more and more about the sky and about the universe, the causes of fear and confusion receded as we understood what eclipses were, as we understood what comets were, and so on. I think now there is no such thing. We understand the universe to a large extent, and as we understand more and more in science in general, of course, what we do not understand and for what causes fear keeps receding. And I think that's a general principle in all of science. Astronomy is no exception. Right? And as people studied the sky initially, of course, for things like agriculture and rituals, but later out of their own interest because of their innate curiosity about what happens around them, people started observing regularities in the motion of the stars, of the sun, of the moon, and even planets. And once they started noting down these regularities and started studying them from century to century to century, they also realized that these regularities weren't constant, but they slowly changed as well. So, for example, if Aryabhatta had made a table of numbers to help you predict eclipses, after a few hundred years, the table seemed out of date. So, why was that so? So then the astronomers who came later had to correct these tables and try and understand, come up with a theory of why they changed and so on. This is how astronomy slowly developed as time progressed. At least partial astronomy developed this way. As time progressed, you notice that what people knew a few hundred years ago was no longer accurate, right? And how did this advance happen? How does this increased understanding happen? It went hand in hand with mathematics, and as you know, at least in Indian context, you might know a bit. Most all the astronomers, famous astronomers in India in ancient times, were also famous mathematicians, Brahmagupta, Bhaskaracharya, Varahamihira, and so on, because maths and astronomy went hand in hand for a long time, and that's true of almost every culture. But then if you look at the last, let's say, 300 years or 400 years, which where has been tremendous advance in understanding the universe, that has been pushed mainly by advances in technology, and I'll come to that a bit later in today's talk and maybe in the next talk as well. So this is just to kind of give you a historical perspective of how astronomy developed from what was probably cultural, a part of culture, to something which is now a science. So now let's start with a bit of what we see. If you go to the night sky and go look, it looks like everything is on a sphere. There's a sphere covering around the Earth, which is this is called the celestial sphere. We imagine this to be a sphere very, very far away, at infinite distance, centered on the Earth. And stars and galaxies and things we see are imagined to be on the sphere, and they move on the sphere. This is a good way to understand and predict what happens in the sky. Uh, on Earth, we know how to define location or tell people where to go, where to come, and where you are, and that is through a grid of coordinates, which we traditionally call latitude and longitude. And if we project this latitude longitude grid outwards up to infinity and make it fall on the celestial sphere, then we now have a celestial coordinate system with which you can now calculate the positions of stars and planets accurately. Right? This this coordinate system, if you project onto the celestial sphere, is called right ascension and declination. Declination is the equivalent of latitude on the Earth, and right ascension is the equivalent of longitude on the Earth. And just as longitude system on Earth is defined with the zero longitude passing through an arbitrary position called Greenwich Observatory, so also the right ascension zero is marked by some a particular position which has some astronomical significance. I'll come to that later. But is this unique? As as you know, a spherical coordinate system is defined by the poles and an equator, but then you can put the pole and the pole anywhere you want to, right? And therefore, there are many other systems of coordinate grids on the celestial sphere. But the one which is used most often is right ascension and declination. There are other systems like the ecliptic coordinate, local coordinates of altitude, azimuth, etc. So how does it work? Our equator projected outwards touches the celestial sphere in what is called a celestial equator. Our North Pole and South Pole, or the axis of rotation projected outwards, touch the celestial sphere on the North Celestial Pole and the South Celestial Pole, and that then defines the coordinate system. So lines parallel to the celestial equator are like latitude are called declination, and the lines parallel to the axis of rotation are called right ascension. Now you might notice on the figure on the left an orange line and the green line. The green line is called the ecliptic, and that is the projection of the Earth's orbit around the sun. And we know that this is inclined at an angle, and I'll come to that soon. Now, the reason I'm talking about celestial sphere is because one of the earliest astronomy for the last 1,500 years, if not more, in all cultures, including India, was about positional astronomy, right? And that's what we'll start with. So, and therefore, but then on the sphere, you need to then calculate angles and positions and distances and how they move and so on. And this is done using spherical trigonometry. And so our planar trigonometry, where all the trigonometric equations will not apply because it's on a sphere. And on the bottom right, I have given, just to kind of impress you, a few formulae from spherical trigonometry. You will notice that is different from planar trigonometry, and therefore one needs to learn this. And that's one of the reasons mathematics and astronomy went hand in hand, because you needed to develop spherical trigonometry in order to understand the movement and positions on the celestial sphere. Now, what are the various motions on the sphere which people have been studying for, let's say, 2,000 years? The first one, of course, is the rotation of the Earth around its own axis. This is a diurnal motion. This makes things rise in the east and set in the west. And we kind of assume it's once every 24 hours. That is not true. In fact, if you look at the rotation of the Earth with respect to distant stars, it's actually 4 minutes less than 24 hours. And that is because the Earth has to rotate a bit more the next day to point towards the sun, because the Earth is going around the sun, and therefore there is a 4 minute difference between the day a day between the sun being on the zenith and the sun being zenith the next day versus the stars appearing the same position the next day. And this 4 minute difference is what gives rise to the fact that we have different constellations at different times of the month. For example, you can see Orion in summer, but you can see some other constellation in winter. You can see the sun moving through the zodiac. All of this is because of this 4 minute difference. And this 4 minute difference is because Earth goes around the sun, and therefore it has to turn a bit more to face the sun compared to the previous day. Right. So this is a very nice. You would have seen videos of the sky moving across the Earth, but then I like this video because this actually is what happens, which is that the Earth rotates around its axis. And given this perspective, I think it's a bit bizarre. Some of you probably have vertigo already. And this is what actually happens in space, right? The stars are kind of fixed, and the Earth rotates once every day. And I like this video because it gives us a very different perspective of of what actually happens, and it's kind of mesmerizing. Uh, the next motion we all are very familiar with is the Earth revolving around the Sun in a slightly elliptical orbit, and that is defined as a year. Again, it's complicated because of various definitions of a year depending on where how you define exactly one revolution. And I given the time it takes in days up to 4 decimal places, but of course it goes on, and and that gives you complications like leap second and leap years, and the fact that in the Indian system you have Adhikamasa and Shrayamasa and so on, because the period the Earth takes to go around its axis and the period the Earth takes to go around the Earth are not integer multiples, they're not simple multiples of each other, and therefore you have various complications of added days and subtracted days, so on and so forth, right? When you look though from of course the Earth goes around the Sun, but from the Earth's point of view, the Sun goes around the Earth, let's say, and therefore the Sun will go around the Earth apparently once a year against the background stars, and therefore the constellation behind the Sun at any point is the zodiacal constellation we say the Sun is in, but this is just an apparent line of sight thing, and therefore the Sun will move through the 12 zodiac constellations or 13 if you look at the latest IAU convention once a year. Because the Earth goes around the Sun, the Earth therefore is the universe therefore appears a little different from, let's say, June and December, and this leads to familiar phenomenon which people have been measuring for the last few hundred years called parallax and aberration. Parallax, basically, of course, you all know, if you know the famous example of where you put a finger in front of your eyes, and then you look at what's behind the finger. When you close each eye, the finger will appear in front of different objects, and that is called parallax. And astronomers have been doing the same trick, except that the distance between the eyes is equivalent to the distance between the June solstice and December solstice. Say, right? The position of the Earth in space 6 months apart. And if you look at a nearby star against the background of far stars much farther away, the nearby star will shift in position once a year, and this gives you a very good method of determining the distance to the nearby star. And this is how the initial distance measurements of the universe were. And this is because the Earth goes around the Sun in a reasonably large orbit, right? Now, of course, we all studied in school that the rotation and revolution planes are tilted at some angle, and this tilt of 23.5 degrees is very, very important for us, for life on Earth as well. This leads to the seasons. If the tilt was zero, you would not have seasons at all. In India, we call because it's tilted, the apparent motion of the Sun northward and southward through the year is called Uttara and Dakshinayana, which you will be familiar with. The length of the day varies throughout the year. As you go more north, the summer days are much, much longer and so on. You get in phenomenon like solstices and equinoxes. And even in the north of the Arctic Circle, the south of the Antarctic Circle, you even get 6 months of daylight and 6 months of nighttime. All of these is because of this angle of the tilt angle not being zero, but at the value of 20.5 degrees. Now people, now astronomers knew all of this much, much long back, right? 2000 years ago in most cultures, right? And they were calculating things based on this. They had calendars and so on. But then after a few hundred years, they noticed that they were out of date, right? What was supposed to happen in June started happening a bit, July, a few weeks later, and so on. And then and at some point, astronomers discovered that there's one more motion they did not know about and they had to correct for, and that is the position of the Earth's axis. So the Earth's axis points towards roughly the pole star, you know that. But then that is not strictly true. The Earth's axis makes a cone, and this cone of revolution takes around 26,000 years to do. This is because of the effect of the moon and the sun on the equatorial bulge of the Earth, because the Earth is not a sphere, right? And because of this, the direction to which the Earth's axis of rotation points will change over 26,000 years. Right now, it so happens to point very close to the star we call Dhruva or pole star, right? And because of this, the coordinate system itself changes with respect to the stars, and therefore our the coordinate values of stars, etc., keep changing gradually, roughly, and we have to correct for it constantly in observatories or with any telescope, even amateur telescopes. And this precision makes your calendars out of date very fast, right? And this also, for example, you might have heard that Sankranti is celebrated around 14 January. in India, but Sankranti actually is happening on 21st December. And this error of 3 weeks, etc., is because we have not updated the traditional calendars in India are not updated for precision. But of course, the official Indian calendar, which was formed by this committee headed by Meghnad Saha himself, corrects for this exactly. But that is the official Indian calendar. In practice, of course, all over the world, in many cultures, including India, festivals and stuff are out of date. Even the zodiacal constellation against which you think the sun is on a particular date is wrong, because these systems are not corrected for precision for almost 1,400 years. Yeah. Now people then started looking at planets and how planets move. Then they discovered very soon that planets do not move very nicely like the moon or the sun. They have very complicated paths. They sometimes go backwards and come back again, and so on. And this is called retrograde motion. And all of this confused people a lot. So then they tried to fit the model to this, and the way they fit the model to this is to say, okay, planets don't go around the Earth in a nice little orbit, but then they go around the Earth, and then they keep making these loops as they go around the Earth. These loops are called epicycles, and they try to refine the parameters for each planet of these loops to match what they were seeing. And the longer they accumulated data, the more the deviations were from the simple models, and they had to keep adding more and more epicycles. So the term wheels within wheels, for example, comes from this, where as you go along and as you get better and better data, you had to add more and more epicycles to account for it, and this orbit became very complicated. And an understanding of why planets should move this way, of course, was lacking. Why would planets keep going, making loop after loop after loop, right? But then it was some cultures knew it was just a model fit, and it wasn't probably real. They did not know how it actually happened. Some cultures, of course, some people thought it was actually how planets move, but they did not know why. And of course, then the entire point of view, literally and metaphorically, shifted with Copernicus when he came up with the heliocentric model. And when you put the sun at the center, all these orbits, all these loops disappeared completely, and all orbits of planets became just elliptical orbits, or just orbits around the sun, right? And the fact that orbits became simpler, much simpler and easy to understand, was a huge was the initial argument in favor of heliocentric model, because it makes sense, right? Of course, there are more and more evidence which accumulated later, and you all know the story of Galileo and his persecution for championing the heliocentric model and so on. And therefore, very soon with Newton's with kinematic models like the epicyclic theory. By kinematics, I mean just the motion. You fit patterns, you fit your model to the observed motion, and just predict the movement alone. That is kinematics. And if you can predict why it happens, then there's dynamics. Right? Dynamics had to wait for Newton's theory of gravity to come. But before that, we of course had epicyclic model and heliocentric. So on. Once Newton's theory of gravity came in, then you could now a priori argue and predict why the orbits should be the way they are. Right? Then you had central force, and then you knew that you knew what the gravitational force between the sun and the planets, and then you can actually predict the orbits of planets, and you can predict deviations from the simple orbits of planets from Newton's gravity. And as time went by, the more and more triumphs of gravity. For example, it could explain the Mercury precession to some extent. Of course, Einstein came and did it much better much later on. One of the biggest triumphs of Newtonian gravity, in my opinion, was the prediction of the planet Neptune. Right? So people knew about Uranus, and then they noticed that the orbit of Uranus was deviating from what they were predicting using Newton's gravity. But they were so confident of Newton's gravity because it was proved right for so long that they hypothesized that there must be another planet outside Uranus which was perturbing the orbit of Neptune. And from the observations of orbit of Uranus, and therefore by looking at the Uranus orbit, the data on Uranus orbit, and what Newton's theory of gravity predicted, they could then say, okay, if a planet exists, which was the cause of this perturbation, that planet should be at this position. And they went and looked at this position, and lo and behold, they actually found Neptune, right, a planet there. And this was a huge triumph of Newton's gravity, because you could use tiny deviations from observations and the theory of gravity to actually predict exactly where the perturbing body would be. And of course, we all know comets. The most famous comet was Halley's Comet, and it's named after him because he was the first first to use Newton's gravity to predict orbits of comets, and then he showed that this particular comet kept coming repeatedly to the same comet which came every 76 years, and so on. All of these were how kinematics then became dynamics following Newton's laws, right? Now, let's look. And I avoided the moon. The moon is, of course, a very complicated object, and we of course we know about the phases of the moon. I won't talk to you about that. But then recently you've been hearing things like super moon and blood moon and red moon. It's in the media a lot. All of these are because the moon's orbit is not as simple as we think. There are a lot of perturbations of the moon's orbit, which happen because of the Earth. We also know that the same phase of the moon has the same phase towards the Earth while it rotates around the Earth. And we know this is because the rotation period and the revolution period of the moon are exactly the same, which is due to tidal locking. Tidal locking happens because of the effect of Earth on the moon, and the moon, of course, in turn causes tides on the Earth. We all know about ocean tides, and the fact that the moon is a much less massive than the Earth leads to the fact that the moon is already tidally locked to Earth, but the Earth to be tidally locked to the moon is going to take billions of years, so that will not happen in time. The animation on the left is actually a series of actual photographs of the moon taken throughout a few days, and you can see that the size of the moon changes because the moon's orbit is elliptical. You can also see that the face of the moon we see slightly changes. You can see a little bit more than half the moon in the orbit of the moon, and all of these were first observed by astronomers long back, and then the explanations came, of course, later. And just an example of the fact that the orbit of the moon is fairly complicated. I'm just showing you one graph on the right side, where you show where the x-axis is the difference of the mean lunation, which means when did the full moon happen, and you can see that that it varies a lot from 2000 BC to 2000 CE, and this variation can be now predicted accurately using our models. Right? The other big celestial event people have been observing in the sky for many centuries are eclipses, and of course planetary conjunctions. Eclipses, again, initially we do not know what they were, and therefore people were scared of them, including in India. But then Aryabhatta himself in the 6th century CE gave an explanation of eclipses based purely on shadows. So the knowledge of predicting eclipses and the knowledge of why eclipses form had existed even in India long back, right? Eclipses, again, when people observed eclipses over hundreds of years, they found again patterns and regularities. These are called Saros cycles, and these cycles occur with various periodicities, and these various periodicities occur because of various roughly multiples. If you look at various periods involved, moon's orbit on the Earth, the Earth's orbit on the Sun, and so on, and their changes. There are various roughly approximate integer multiples which happen now and then, and these various integer multiples give rise to various periodicities. There's a periodicity of 18 years, there's a longer periodicity of few thousand years, and so on and so forth. Right? And the animation I'm showing is the path of total eclipse, and you can see the total eclipse path seems to have some periodicity, and that periodicity again is from one particular cycle, Saros cycle number 136. There are, of course, many such cycles, and understanding these cycles without the theory of it was done long back. The Babylonians had observed these cycles and had cataloged these cycles, more around 3,000 years ago. Much later, people like Aryabhatta and others in Greece and in Italy came up with models of predicting the eclipses a bit better. And of course, since then, we know exactly why they cause. And now we can predict them with very high accuracy. Planetary conjunctions of our planets come very close together. And again, people thought that they were a portent of ill omen. But now, of course, we know that it is happenstance alignment of planets as seen from the Earth while the planets are orbiting the Sun. And these happenstance alignments do not mean anything, but of course beautiful to see. And on the left is this very famous Jupiter-Saturn, the Great Conjunction, which happened 3 years ago. And I hope some of you saw it through a telescope. Right now, what else do we see in the night sky? We see the Milky Way. Right, most of you who are living in cities probably never seen the Milky Way. And the top left photo shows you how the sky looks at various levels of light pollution. In Bangalore, where I am, for example, you see like a few tens of stars where the sky is clear. But if you go to an excellent dark sky where observatories are, then you see thousands of stars, right? And then you see this cloudy strip across the sky, which is called the Milky Way. In India, we call it Akash Ganga. We see also meteors. If you go out and lie down and just look at the sky from a reasonably dark side, you'll see a lot of you'll see sporadic meteors coming and shoot. They call shooting stars, and certain times of the year you'll see a lot of meteors coming. These are called meteor showers, right? Uh, we also know, of course, that stars rise in the east, set in the west, and if you take and these star trails are very famous photographs you might have seen. If you open a camera and expose it for a few hours, you'll see these stars trailing, and you'll see that they are all making concentric circles about a point. That point, of course, marks the point where the axis of rotation of the Earth cuts the celestial sphere, and the pole star happens to be very close to that point in the North Pole. Right now people started looking at stars. Uh, Again, they started noting down the stars' positions because remember they have a coordinate system on the sky, and they noticed that the stars and constellations seem fixed. Right? We all know Orion, we all know Ursa Major. They don't change at all, and they don't change for thousands or 10,000s of years. Right? And that is because they're very, very, very far away. Any motion these stars might have in 3D space, we do not see easily because it's very, very far away. But then with advent of telescopes, and very soon after telescopes were started being used by astronomers, people noticed that there's some stars which seem to move from month to month or from year to year, right? And a very famous example is Barnard star. And people are wondering what this movement was, and they very soon realized that this is the movement of the star in 3D space, right? And because they're very, very close to us, or that particular star has a very, very fast velocity, you can see it changing over a few years instead of waiting for tens or thousands of years. But then, of course, a star does not just move on the sky. A star has a velocity vector in 3D, so you can decompose the star's velocity into that on the sky, which is called proper motion, which is what you observe, and that towards or away from us, which had to wait till we had spectroscopy and therefore Doppler shift for us to measure that, right? So for a long time, people were measuring only proper motion, which is the motion on the sky, the transverse velocity component, right? But then now we know the 3D velocity vectors of almost all the stars near us, and therefore we can then predict what will happen. So, for example, on the left is the famous Ursa Major, on the right is Orion, and if you look at Orion, we can predict how the stars would move, and therefore Orion from 50,000 BC to 100,000 CE, this is how Orion appears in the sky, and that's because the stars move very slowly on the sky, but of course they move really fast as we all go around the center of the galaxy. And if you look at Ursa Major, on the left, the time starts from 80,000 BC and it will go on till something similar in the future. And you can see the way the Ursa Major appears in the sky changes. But also you can see some stars are moving really fast, right? Really fast in the sense that they can look at their motion every few thousand years, right? And this again tells you that the nearby you can actually measure the motion of nearby stars, and people are doing that very soon after telescopes were invented, right? So all of these, what I talked to you about is kinematics, right? How things move in the sky, and this people could do without any complicated equipment, and but then this took around 2,000 years to study, to understand, to model, and also to become more and more precise, so you could predict things more accurately. Right? Now we'll come to stars. Right? Now we all seen again. You might have seen a few stars from a city, but then if you go to a dark sky, you can tell the stars are different colors. Even Orion, for example, Betelgeuse is bright red, Rigel is bright blue, and so on. And if you take a star trail picture like I'm showing you on the right, you can very clearly see the stars are different colors. Now, why should they be of different colors, right? And stars also have different brightness, right? Some stars are very bright. Sirius is the brightest star in the sky. Some stars are very, very faint, right? Now, of course, stars being of different brightness is easy to understand. The two possible explanations: some stars are either very, very bright, and some stars are intrinsically very faint. And of course, if you take two stars of equal brightness and one star is very far away, it will look dimmer because of the inverse square law. And of course, one can easily guess that both these effects come into play. So different stars are of different intrinsic brightness and at different distances, and therefore how bright a star looks on the sky is a combination of both factors. But then, and that's something people knew long back, right? And therefore, people had Hipparchus in a few hundred BC in Greece had then tried to classify stars based on their brightness as seen on the sky. And one interesting thing about human perception, be it brightness with the eyes or even loudness with the ear, etc., is roughly logarithmic. For example, if you think something is twice as loud or 10 times or twice as loud, it's actually not exactly linear, or 4 times as loud. the scale is not linear, it's actually logarithmic. The same goes with brightness of the eye, right? And therefore, he had invented a linear scale of brightness, where magnitude 1 was one of the brightest stars, and magnitude 6 was the faintest star you could see. But then, and this linear scale later we found was actually logarithmic, which means that if there's a difference in magnitude of 5, it actually corresponds to intrinsic brightness of a factor of every of 100, right? For every unit of magnitude. And therefore, apparent magnitude is how bright it looks as seen on the sky, which is a combination of two factors, of course, how far away the object is and how intrinsically bright it is. But then how do you then compare stars? If you say one star is brighter than the other, I want to know what the intrinsic brightness is. Tell you exactly how bright the star intrinsically is, right? And therefore, there's a standard distance we assume, and then you can calculate if you put a star at that distance, what will be the magnitude? That's called the absolute magnitude. And therefore, apparent magnitude is what you see on the sky. Absolute magnitude is then gives you the actual luminosity of the star, right? And if you know the apparent magnitude and absolute magnitude, in principle, you can get the distance to the star, right? Because of the inverse square law. Or if you know the distance and the apparent magnitude, you can calculate how bright the star is intrinsically. And there are various, and for some stars, you can get the distances and the apparent magnitude. For some stars, you can get the absolute magnitude and the apparent magnitude, and therefore you can calculate one or the other. And that's something that has been going on for a few hundred years, right? Now, you can also tell, for example, not understand till 1800s when astrophysics came into the picture, and we had some understanding of thermodynamics, right? And so I'm going to skip a bit into the next lecture and come back. So people later realized in 1800s that if you look at the spectrum of a star, it's roughly a black body, and I suppose all of you know what a black body is, and you know that in a black body, the higher the temperature, the higher the frequency of the peak of the emission, and therefore people soon realized that the colors of stars were nothing but a proxy for the surface temperature, right? And therefore, a very hot star would be blue, a slightly less hot star would be bluish white, and even less hot star would be yellow, and then orange and then red. So red stars are cooler than blue stars, and that is also reflected in what is your, I mean, what you should see on Earth. In practice, of course, we always paint red as hotter than blue in popular culture, but we all know as physics students that is wrong. Blue, if you heat up a metal, it will first appear red, then yellow, and then blue. And similarly, stars as well, right? So a red star like Antares or Betelgeuse is around 3,500 Kelvin on the surface. The sun is around 5,500 to 6,000 Kelvin on the surface, and therefore it appears a bit more yellow and white. And stars like Rigel are much hotter at 25,000 Kelvin, and therefore they appear blue. And therefore, color of a star is proxy for temperature. And if you notice, a star is not too hot, is not too cold, is just about in the middle, like Goldilocks, right? Now people also knew for many hundreds of years that some stars change their brightness. And a very famous example is Algol in the northern sky. Algol is a star which changes in brightness over 3 days or so, quite dramatically, right? And much later, people knew that it was because Algol was two stars going around each other, and when they of very different brightness, and the brighter star comes in front of the fainter star, of course, there's a slight dip in brightness when the fainter star comes in brighter star, and so on. And when they far apart, then of course you see the sum of both the brightness. Right? The various kinds of variable stars. The light curve at the bottom is that of Kuiper-Percy, which is a Mira type variable. And the fact that Kuiper-Percy varies very dramatically and very regularly is because the star is pulsating. Okay? And the fact when it pulsates, of course, its total luminosity changes because its diameter changes. So the various kinds of variable stars, some are because the star intrinsically changes in brightness because it pulses. Some stars change in brightness because they're actually binaries, and we are looking at it as one single star. But as they eclipse each other, total light changes. You all might have been aware of something which happened in 2019. It came in the papers, that of Betelgeuse, which is a bright red star in Orion, which dramatically dimmed, and people thought, oh my God, it's going to become a supernova, but that is not true. It just happened to expel a dust cloud which blocked some of the starlight and became dimmer. But we also know that Betelgeuse could go supernova anytime between now and, let's say, 10,000 years, which is very exciting. There are more examples historically of stars changing their brightness, a lot more dramatically than what I showed you. For example, nova nova means a new star, right? So Kepler and Tycho, for example, observed suddenly there was a new star in the sky. And these were, and for example, Tycho star was a supernova, Kepler star was a nova, and so on. And people also, and the famous example, of course, is in 1054 AD, where the Chinese astronomers, and now we know certain other astronomers now, which we now know as the Crab Nebula, which is what you see on the top right, taken from the HST. And this is because of a massive star exploding because of the exhaust of fuel, and I'll talk to you a little bit about that in the second talk, right? And therefore, when a supernova explodes, it can be as bright as the entire galaxy for some time. The top middle picture is that of a galaxy, and the bright star you see on the bottom left is actually the supernova. And you can see that the supernova was actually as bright as the entire galaxy for a few days. And the bottom animation shows you another supernova, where these are, which actually the pictures taken a few days every few days, and the curve on the right tells you how bright it is, and you can see that the brightness dips very sharply. But then at the supernova, at the first day or two, it is actually as bright as a galaxy. It can be incredibly bright, right? And therefore, people had observed novae, not supernovae historically, because supernovae in our galaxy are very rare. And again, people did not know what they were. They said it's a new star and so on, and had to wait for astrophysics to come in to help you understand why this happened, right? Now, the other thing we see in the sky, of course, is Akash Ganga. I see we're running out of time, so I'll go a bit fast because I want to tell you a little bit about telescopes in India. Akash Ganga, or the Milky Way, there's no way you can see it from a city because we have too much light pollution, but I suggest you go to a dark sky, and it's brilliant, it's beautiful. We now know that it's our own galaxy. We are in the middle, we are inside of, and if you look at the right picture, you'll see that the sun is marked somewhere at the bottom, right? The sun is not at the center of a galaxy, it's much farther away, it's around 2/3 away. And the galaxy itself is we know how big it is, it's around 80,000 light years across. The sun is around 24,000 light years away from the center. And because our galaxy is like a disk, and because we are in the disk, we see the galaxy all around us. And of course, the galaxy, we see more stars towards the center of the galaxy than away. And this leads to this band of light we see around us. And of course, the band of light is much more dense towards near the center of the galaxy than exactly the opposite direction, right? And of course, Galileo, when he first pointed his telescope to the galaxy, resolved the Milky Way into individual stars, so he knew that the Milky Way was made of individual stars. Of course, he did not know what a galaxy was, and soon after they also found nebulae or gaseous nebulae along with these stars as well, which I'll come to shortly, right? Uh, so what is in our galaxy? What did people see in our galaxy before the advent of large telescopes, right? So with small telescopes, people found that there were these fuzzy objects, which were then seen to be made of a few stars. For example, on the left hand side, you see an example of a globular cluster. In the middle, you see an open cluster. Or the middle example is that of Pleiades or Seven Sisters, which is Kritika in India. And on the right, you see a close-up, a telescopic view of a star which is seemingly single, but then if you look at it closely, it's a binary star, right? So we know that stars now occur; they don't occur singly all the time. The sun is a single star, of course, but stars form in pairs. Stars form in loose groups like Pleiades. Stars form in dense groups called globular clusters, and all of these go around the galaxy, but they're not torn apart because they're bound by their mutual gravity. And so, as a unit, they go around the galactic center in their orbit, but then they are bound together by their own gravity, right? Uh, Around 1700s, people already started seeing fuzzy objects on the sky, and these they call nebulae. Nebula is just a word for a gas cloud. On the left is a famous picture of the Orion Nebula, which is where stars are being formed. In the middle is an example of a planetary nebula, which is what our sun will become after 5 billion years. And on the right, you see an example of a supernova element, which is what happens if a star which is more than 8 times more massive than our sun explodes. And after a few thousand years, the outer layers explode and expand enough to form a supernova remnant, right? Of course, these are all pictures from the Hubble Space Telescope, but then 1700s and 1800s, astronomers painstakingly studied them, trying to find out what they were. They were mistaking them for galaxies and so on and so forth, and all that confusion got resolved slowly. So this is again something people saw in our own galaxy with small telescopes, right? And later, people also started looking at objects which were not like this, like fuzzy like this, but a bit more compact. And these then later we know now as other galaxies. For a long time, till the early 1900s, people thought our galaxy was the entire universe, right? And it took some advances in astrophysics, which I tell you about the next talk, where people then go measure the distances to some of these island universes, they found out that these are external galaxies. And now we know that galaxies come in various shapes and sizes. We have elliptical galaxies, spiral galaxies, irregular galaxies, and so on. We know galaxies can also merge with each other. Now, why is that so? That of course we now understand because of gravity. A galaxy is held together by spiritual gravity. But why should they have different shapes? That depends on the velocity of the galaxy. Just like the Earth doesn't fall into the sun or the moon doesn't fall into the Earth due to because it has a velocity which prevents it from falling in due to gravity. Same way, the motion of the stars inside the galaxy counteract the gravitational attraction towards the center, and therefore they keep it stable. In elliptical galaxy, the stars move in random directions. In a spiral galaxy, they have more regular orbits and they are in a plane and so on. And now we understand why different galaxies form different morphologies and what keeps them stable against collapse, and how in fact if you merge galaxies, you can go from one morphology to the other. Right? And I'll talk to you a little bit about that if there are questions. Now that kind of ends what I call astronomy, which is what you see, what you can observe in the sky without telescopes and with telescopes, without necessarily understanding what causes them, what science is behind them, but basically what you can see and what you can observe over a longer time. Now I'm shifting gear a little bit because I was asked to talk a little bit about astronomy. Oh, sorry, I'm just going to put my battery on. Give me a second, please. Now, of course, we know all of what I told you because we have telescopes and detectors, right? And for a long time, from let's say 3000 BC till around 19 late 1930s or mid 1930s, we only observed the universe through what we call visible light or optical waveband, right? Because that reaches the Earth, the surface of the Earth. And then around 30s, we started looking at the universe in the radio because Carl Jansky famously discovered that he got radio waves from outside the ground, and radio and optical and a few bands on the other side are the only light wave bands which can reach the surface of the Earth. Everything else is absorbed by the atmosphere, and therefore, if you want to observe gamma rays or X-rays, ultraviolet or microwaves, you need to put telescopes into space, and that is something we all know. Now, why do you want to observe? Why do you want to observe the universe with gamma ray, X-ray, ultraviolet, etc. up to the radio? There's no need to do so. You might assume that if you look at a galaxy in a visible light, that's all the information you got. But that's not true because remember, all of these wavebands differ in energy alone, nothing else, right? And therefore, different energy photons arise from different physics phenomenon, and therefore, if you look at a given object, let's say the Crab Nebula in different wavelengths or frequencies or wavebands, like you see the top picture, different waveband, the photons from different wavebands arise in different processes, and therefore from different parts of the object, right? So on the left, for example, the radio comes from electrons gyrating in the magnetic field and therefore producing synchrotron emission, which is non-thermal, right? Gamma ray comes from a totally different phenomenon, and so on. X-rays come because of the energy produced by the pulsar inside, which hits the nebula outside, and so on and so forth, right? The bottom right, you can see two pictures of what is famously called the Eagle Nebula or Pillars of Creation. On the left is the Hubble Space Telescope picture of this nebula where stars are being formed deep inside. And the fact that you can't really see the stars is because of the dark band, the dark dust obscuring us, because dust obscures or absorbs optical waveband. But the same thing if you look at infrared, which is what is seen on the right side. Infrared can penetrate dust, and therefore you can see inside, and therefore what looks dark looks bright, because then you can see inside the dust and look at where stars are being formed and so on. Right? Therefore, to understand a particular object or particular phenomenon in detail, you need to observe it in all wavebands. Right? Just as, for example, if you want to know what a human is made of without cutting them open, X-rays will tell you that it has a skeleton. The optical tell you I have a skin. Infrared will tell you I have blood vessels inside with heat. Ultraviolet will show you tissues and so on, and you put them all together to have an understanding of what an object is made of. Similarly as well. This is why we need telescopes of different wavelengths. So I'm going to tell you a little bit about the institute I'm from and then about India. Both the institute I am at, Indian Institute of Astrophysics, traces its origins to 1786 to what is called the Madras Observatory. We now run four observatories, one in Ladakh, which you might have heard of, in Hanle, which has optical, near infrared, and Cherenkov gamma ray telescopes. We have a more than 50-year-old observatory in Kavalur called White Observatory. Kavalur is near Vaniambadi in Tamil Nadu, which has optical telescopes. We have the Kodaikanal Solar Observatory in Tamil Nadu again, which has been running since 1899. We have the Gauravito Radio Observatory. I'm really sorry, solar should become radio. Gauravito Radio Observatory, which is around 2 hours north of Bangalore, which currently looks mainly at the sun through radio telescope, but also has some telescopes to look at pulsars and so on. And then we have a campus in Hoskote near Bangalore, where it's a technology center where we make space payloads, and we also run the Himalayan Chandra telescope, which is in Ladakh remotely from here, right? And so I just want to show you a few pictures because telescopes are beautiful. These are the telescopes in Hanle in Ladakh. On the top left on the mountain of Dikpa Ratsari, you find the Himalayan Chandra telescope and the Growth India telescope, which observe in optical and near infrared. In the bottom, you see the Hagar on the left and Mace on the right. These observe gamma rays indirectly by observing the Cherenkov radiation, which are these flashes of light lasting for microseconds in the atmosphere when the gamma ray hits an atom or a molecule in the Earth's atmosphere. And this is a flyby drone footage of the observatory in Ladakh. And you can see it's extremely beautiful place. And the reason we are here is not because it's beautiful, but because the sky is very dark and the sky is very stable as well. It's one of the darkest areas in India. And that's why we have the telescope there. And more people, including ISRO, are putting up telescopes at the site to take advantage of the conditions here. And in fact, the Cherenkov telescopes are done in collaboration with BARC and IIRS as well. The other telescope site we have, observatory we have, is in Kavlu in Tamil Nadu. This used to house the 2.3 meter Vainuvappu telescope. This houses the 2.3 meter telescope, which used to be the largest till the 3.6 meter telescope came up in Nainital. And this hosts a number of telescopes, for example, the Vainuvappu telescope, the JCB telescope, the 1440 inch, and so on. And you can see all of those telescope domes here. This is in the middle of a forest, and it's again a beautiful site. It used to be a very, very good site astronomically. Now the weather conditions have degraded, but still these telescopes are still operational and are being used by astronomers. Now let me kind of go outwards to all of India. So like I said, India has a number of optical and NIR near-infrared telescopes in Kavlu, for example, or Ladakh. IIRS, which is an institute based in Nainital, has observatory site in Nainital, and Devastal, this is in Uttarakhand. And currently, the two largest telescopes in India are in Devastal. One is a 3.6 meter telescope, which is completely movable. You can look at anywhere in the sky. And the recently commissioned 4 meter liquid mirror telescope, which can only look up at the zenith because you cannot move. And this is basically a tub which has liquid mercury, and the tub is spun up at a constant rate so that the surface of the mercury takes on a parabolic shape, which is and therefore it's 4 meters big. On the other hand, you cannot tilt it because of liquid mercury, and therefore you can only look at a zenith. Right? We have Guru Shikhar in Mount Abu, Rajasthan. There is a telescope, this observatory site run by PRL, which is again under ISRO, and this is a very old site which observes primarily in the near infrared because it's very, very dry out there. We have solar observatories. We have Udaipur Solar Observatory in Rajasthan, which is in the middle of a lake. We have the Kodaikanal Solar Observatory, which is run by IIA, like I said, which dates back to 1899, and so on and so on. And there are many telescopes which are 1 meter and smaller across India. In the gamma rays, we have, of course, the Mace and Hagar in Ladakh. These, again, do not observe gamma rays directly, but they observe the flashes of light called Cherenkov radiation, which lasts for microseconds. In the Earth's atmosphere. And then we have a very different telescope in Ooty, run by TIFR, called Grapes 3 in collaboration with Japan, which also looks at cosmic rays, right? Not just gamma rays. Cosmic rays are particles like electrons and protons and so on, which when they hit, which come from space, and when they hit the Earth's atmosphere, then there's a shower of particles which have less energy, and the shower of particles imaged by Grapes 3, and then you reconstruct where the original cosmic ray came from and how much energy that has. Right? And of course, India has been very, very prominent in the world in radio astronomy. We have some of the largest telescopes in India. You might have all heard of the giant meter-wave radio telescope, or GMRT, run by NCRA in Kodak, which is near Pune. It's one of the world's largest telescopes. It has 30 dishes. Each dish is 45 meters in diameter. You can see the car here for scale, and it's spread over 25 kilometers. And it functions, and it's an imaging telescope. And the reason it's spread over 25 kilometers is because you can use a technique called radio interferometry to make images as if you had a single telescope of 25 kilometer diameter, in terms of how fine detail you can make out on the image. And this can now observe continuously from 125 megahertz up to 1500 megahertz. Of course, a much older telescope in the radio, which has been operated by NCRA since early 1970s, is the Ooty Radio Telescope. This is a gigantic telescope, which is half a kilometer in length, and it's on the slope of a hill in Ooty. And this, when it was built, it was the world's largest telescope, and it's still one of the world's largest telescopes. It was one of the major achievements of it when it started, when it was operating in the late 70s and early 80s, was to provide very strong evidence for the Big Bang model as against steady state. And then it's been used for the last 20 years to study what we call space weather, or what happens when the sun emits plasma magnetic fields and how it travels between the sun and the earth. And this is something which ISRO itself is very, very keen on studying, because when this plasma magnetic field comes near the earth, it can damage or affect our satellites in space, which depend on electronic communication. And a lot of work done at the Ooty telescope has helped us understand the space weather or solar weather much more. It's now being upgraded to do a lot more than what it's been doing so far. Okay. Now we also have telescopes in space. It's not just on the ground. As we said, if you want to observe ultraviolet or X-ray or gamma ray, you have to go into space. And one of the more important telescopes we have is AstroSat, which was launched in 2015 by ISRO. It has 5 payloads, all of which can observe simultaneously in the same direction. And between the 5 payloads, you have almost continuous coverage from ultraviolet to soft X-ray to hard X-ray. Some of these instruments can make images. Some of these instruments can count photons very precisely and tell you where it came from. In the bottom is the complete AstroSat after integration in ISRO with this foil around it. On the right side is one of the payloads, which is the ultraviolet imaging telescopes. The payload you see, this is made in Cresco Cotate by my institute, and what you can see is the engineering model, which is to scale, right? And this is exactly the replica of this was flown on AstroSat. AstroSat continues to function. It's now it's more than 7 years old, and it continues to function really well. And we still continue to get really good data, and a lot of work has been done to understand the universe in high energy, both by Indian astronomers and by astronomers around the world using data from AstroSat. What is coming up soon? Of course, you might have heard in the papers about LIGO India. LIGO India is going to be a gravitational observatory, just like the 2 LIGO observatories in the US. And this is going to come up in Hingoli, which is near Nanded in eastern Maharashtra. The funding has been approved, so they can start construction, etc. soon. Aditya L1 is a solar space mission which will be launched anytime soon by ISRO. This has 7 payloads to study the sun. This will be at the L1 point. L1 is a Lagrangian point, which is between the Earth and the Sun, but very, very, very close to the Earth, and this is a stable point for spacecraft to be in. And this can point towards the Sun all the time. It has 7 payloads, some of which will image the Sun both in white light and spectral line and so on. Some of these will actually measure things in situ. I told you about solar storms or flares which come towards the Earth, and when they come towards the Earth, they pass through Aditya L1. And therefore, you can measure the magnetic field or the plasma properties as it passes over Aditya L1. And therefore, we have both in situ measurements instruments as well as remote imaging instruments. ISRO also going to launch something called XPOSat very soon this year. This is an X-ray payload to X-ray, and this is going to look at polarization in the X-rays from celestial objects, and that will be launched very soon. There are a lot of projects coming up in various stages of planning. For example, the National Large Solar Telescope, INSIST, is a next generation ultraviolet telescope which is being planned. The National Large Optical Telescope and so on. All these are on the proposal stage, and hopefully we'll see them operational, let's say 10 years later. India is also part of upcoming facilities which are international, because really, really large telescopes are too expensive and too complicated to be built by one country. A very important telescope we are a part of is called 30-meter telescope, which is supposed to come up in Hawaii. It's a telescope being made by 5 countries together, and India is a partner. India's contribution is in kind, which means that we supply parts of the telescope. We make mirror blanks and we get mirror blanks and we polish them. We make support assemblies for all the mirrors. So remember, this is a 30-meter telescope. You can't have a single mirror which is 30 meters big, and therefore it's made of around 480 odd 1.4 meter telescopes, each of which put together form a 30-meter aperture. Each of these 480 odd 1 meter, 1.4 meter mirrors need to be supported and aligned with respect to each other. All of those support assemblies are being made in India. Some of the mirrors are being polished in India. The sensors which tell you exactly where each mirror is are being made here as well. And of course, we're also designing and writing the observatory software. So a lot of work towards the telescope is coming from here. and the site is supposed to be in Hawaii, though there is yet to be confirmed in a year or so. This is we are a part of is the radio. As I said, India has a lot of experience and skill in radio astronomy, and the largest telescope in the radio is called the Square Kilometre Array. It's going to be the higher frequency part is going to be in South Africa, and the lower frequency part is going to be in Australia. India is one of the founding members of this consortium. There are around 15 plus countries which are a part of the Square Kilometre Array, and we are responsible for the control monitoring software as well as building some of the electronics and some of the feeds and receivers for this as well. So I'll stop here. So I hope I've given you some idea about how astronomy started, what were the phenomenon people could detect with the naked eye for many hundreds of years, how they used and how they saw patterns in them, how they use these patterns to then understand what is going on in terms of kinematics or at least movement, and therefore predict what will happen. Famously, of course, like eclipses. And as telescopes came in, we could measure motion of objects a bit more precisely, and therefore you had better and better models. And for example, and once Newton's gravity came, we could actually understand the kinematics, and we moved to an area of dynamics, which could then explain why and how stars or planets orbit the way they do. The next talk, I will then move to astrophysics, which is basically with the advent of spectroscopy. And with spectroscopy came, thermodynamics, and then later statistical mechanics and quantum physics, and how that impacted what we know about the universe in very profound ways. So I'll stop here for questions.